we're going to discuss how derivatives of a function tell us different features of a graph of this function. So because the derivatives are involved, so this is considered as some application of derivatives. All right, so the first thing we want to talk about is the increasing, decreasing behavior of a function. So let's look at the graph of a function here. Say this is a graph of x. We can see on some part of the graph, the graph is rising. Other part, graph is dropping. So this is in mathematics, we consider function is increasing over here, function is decreasing here. If we compare value, value decreases, here value increases. All right, so there's a mathematical definition in the textbook, so we're not going to talk about the exact definition of increasing function, decreasing function. Right? Just understand what we mean. It's clear from the graph. Now the main thing is we want to explore the relation between the increasing, decreasing behavior and the derivative, or more precisely, the sign of the derivative function. All right, so, well, here's our result. Basically, this says if derivative is positive, the function or graph of function will increase. If the derivative is negative, graph function will decrease. There's again rigorous mathematical proof of this result. But then again, here we're going to just look at the graph, get some idea, why this is the case. All right, let's examine this section of the graph. Clearly, it's increasing. Now, how we can tell, the sign of the derivative of function over this portion? We can examine a tangent line. All right, so just draw tangent line over this section, any point. You can see the tangent line rises. The straight line rises. What does it mean? It means the slope is positive, right? Slope of straight line positive, the line increases. Okay, but slope of tangent line is a derivative. So this tells us derivative of function must be positive. All right. Of course, if derivative is positive, and slope is positive, then tangent line increases. So either way, you can see it is true when function increases, the derivative is positive. The reverse is correct too. Okay, this kind of verified graphically. It is true when the derivative positive, function increases. Similarly, over this blue section where the graph clearly is decreasing, if you draw any tangent line to the graph, the line declines. It means slope of the line is negative, but then again, slope of tangent line is a derivative, so derivative is negative. This again kind of verify the result here. Okay, so this is what we are going to rely on to determine increasing, decreasing of a function. So how do we exactly do it? How do we, given a function, how do we actually do it? Well, first of all, we're going to find all critical points by solving f prime equal to 0. right? And from the graph up here, you can see too, those intervals where function decreases or increases are divided by actually critical points. It's not a coincidence, it can be proven, all right? So this just tells us all we need to do is to find all critical points. Solve f prime equal to 0, and then create a sign chart for f prime. Say you find the critical point at C1, C2. So on a number line, you divide the number line with the C1, C2, right, into 3 sections. Then check the key, check the sign of f prime, because we care about whether f prime is positive or f prime is negative, right? So how we check is from this interval we pick up any value. Don't pick up C1 or C2, because if you do, you get 0. You don't care about the C1, C2. You already know at the C1, C2 f prime is 0. You want to check the interval over here, over here, over here. How you do it is pick up a test point, any number, pick it up, plug in here for x, see f prime, see if it's positive or negative. If it's positive here, then the derivative will be entirely positive over here. Again, say if you check that point between C1 and C2, say it's a negative, then you will know from C1 to C2, f prime will be entirely negative. Similarly, say you find out it's going to be positive here. This is just a hypothetical, illustration of a sign chart. It could be positive and positive, and here become negative. So whatever sign chart you come up with, well, you're going to determine accordingly, okay? So this is how we are going to do it. Let's see one example. So here, find the intervals of increasing and decreasing for this function. Okay, so like we discussed, we're going to first find all critical points. Remember how to find the critical points? You can set f prime to 0. So find f prime, differentiate 15x squared, differentiate, you have 15x to the 4th power. And then factor out the 15x squared, you have 1 minus x squared here. Okay, set it to 0. Set the derivative 0 to find the critical point. So simple algebra, you're going to find the 0, you're going to find the 1, you're going to find the negative 1. Or as I call it, C1, C2, C3. Because those solutions is what we call the critical points. So that's called the C1, C2, C3. Okay, find all critical points. We just did that. Then do a sign chart for f prime. So on a number line, you mark your critical points. Negative 1 is 1, 0, and 1. Test f prime over each subinterval. 1, 2, 3, 4. There are 4 of them. So for example, if you're going to test out this section, you're going to pick up a value from on the left side of a negative 1. For example, you pick up a negative 10, negative 5, negative 1.2, negative 1,000. Any number on this side is fine. And let's just pick up a negative 10. Now, negative 10, plug in for x here. Remember, you're going to plug in here in f prime. Where's our f prime? Here's our f prime. You're going to plug a value in here, okay? Because this is for f prime. Negative 10, right? Negative 10 plug in. Well, you can use your calculator. It's going to be negative. All right. Now, between -1 and 0, we're going to pick up some value here. Okay. As which one? Pick up any one. -0.5, -0.003. Use your calculator. If you do that, you can find out the value is positive. So I can just write and say, if you do f prime at negative 0.01, guarantee you with your calculator, it's going to be positive. Well, here we picked up f at say -10, right? Again, use a calculator to do it. You're going to find out it's going to be negative. Anyway, so this is how you try to create a sign chart or sign distribution. Okay, so between 0 and 1, again, we're going to pick up, say, 0.1 to test out. 0.1, test out the f prime. It's going to be, again, use a calculator. I can guarantee you it's going to be positive. On the right side of 1, this interval, we can pick up, say, 1,000. All right, any number is fine. Any number on the right side of 1 is fine. So we pick up 1,000. 1,000 plug in, again, use a calculator. Plug in here, of course. Make sure you plug in here. Okay, it's going to be negative. All right, so we got our sign chart. With the sign chart, then we can tell the graph will decrease. This is what we want to say. The graph will increase, the graph will increase, the graph will decrease. That's our answer. Now we know, for example, from -infinity to -1, graph function will decrease. From -1 to 0, graph will increase. We're not looking at the graph, okay? We are trying to do it in the dark based on sign of derivative, okay? That's the whole point. Then again, 0 to 1 function will increase, 1 to infinity function will decrease. Okay. So this is one thing we can tell based on the sign of derivative, increasing, decreasing. Now, there's more we can do with the derivative. So next, we're going to introduce the first derivative test. This test allows us to detect any maximum value, minimum value at each critical point. Okay, so basically the result says you find the critical point. You find the critical point to C. If your derivative is negative, or if your derivative is positive, let's just mark it. This was clear. Positive on the left side and the negative on the right side. Then FC, function value at this critical point C, is going to be minimum. Or if f prime is a negative on the left side and the positive on the right side, FC will be maximum. Why is that? It's kind of confusing to remember what's what, right? It's easier to see the graph, especially after you come up with your increasing, decreasing. All right, let's see. So you still have to do a sign chart, you see here. So you do a sign chart, say in this case, we find it the positive, right? On the left side, what it means is graph will increase. Graph will decrease. Oh wait, this is decreasing, this is increasing. No, I think the result is the opposite. But anyway, let's not not even claim anything yet. Okay, so first derivative test, right? So we do the sign chart. So first case, say the derivative is positive on the left side here, and the negative on the other side. And then of course, accordingly with the sign chart, we know it's going to increase, it's going to decrease. Then function value will be a maximum. Will be a maximum. Right? That's actually correct result. Why is that? You don't need to memorize. All you need to do is to follow the arrow, so going up and down. So somewhere here you can see you expect the highest locally highest point on the graph, which means it's going to be a maximum. Much easier to remember the result this way. Okay. Similarly, if your sign chart is that f prime is negative on this side, so it just means the graph will decrease, and this side graph will increase. Then again, with the increasing, decreasing, the arrows, you can just follow the arrow coming down, then up, then you expect what? Minimum. So you can see this result really is a byproduct of the increasing, decreasing result, which we always do anyway. Once you come with the sign chart, then you'll be able to just follow arrow to determine what's the case. You can expect the maximum or minimum. Okay, so here we summarize the steps to apply the first derivative test. Find all critical points by solving f prime equal to 0. Say you find the C1, C2. Then create the sign chart. Say you get positive here, negative here, positive here. And then just on the sign chart, you can see the graph will increase here, or decrease here, or increase here. Even though increasing, decreasing is not what we're interested in applying the first derivative test to detect any maximum, minimum. We need to do it anyway. Okay, so with the increasing, decreasing behavior, we can tell, for example, in this case, we expect the maximum at this location. We expect a minimum at this location. C2 is not a minimum. C2 is just a location. The actual function value would be the maximum or minimum. Okay, C is just a location, C1 or C2. All right, let's see an example. We're going to use the same function. This way we don't have to repeat same kind of work each every time. So again, we are dealing with f of x as a 5x to the third power minus 3x to the fifth power, the same exact function. We use there to create the sign chart. And then with the sign chart, we don't have to do it again, the computation. So again, the steps, let's follow the steps. I just explain, first find our critical points. We already did that. Okay, so just to refresh your memory, we set f prime to 0. Find the derivative f prime. Set in the solve, we find all those critical points. Then create a sign chart. Along the number 9, you mark the critical points, -1, 0, 1. And then you do a sign chart, which we did. Okay, so let's recall our sign chart. Negative, positive, positive, negative. All right, so let's just copy out the result. Negative, we use a different color, so let's use the same. we had a negative, 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 positive, 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 negative. Okay, that's what we got before. Then we can tell it's decreasing, increasing, increasing, decreasing. So that's what we got before. Let's just be sure. Decreasing, increasing, increasing, decreasing. Oh, all right. Now, the main thing, okay, with the increasing, decreasing behavior showing here, we can tell at -1, we expect a minimum. What? See, follow the graph, follow the arrow. Decreasing, coming down, then going up. Therefore, at -1, we expect a minimum. And this is the minimum value. So this minimum value is attained at -1. Okay? So this is minimum value. How about at 0? At 0, well, cross 0. Well, the left side, the function is increasing. The right side function keeps increasing. So there's no change of increasing, decreasing behavior. This case, we just don't know. Let's check out our result. If we can only tell, okay, back here, first derivative test, we can only tell if f prime, the sign of prime, changes the sign crossing a critical point from positive to negative, or from increasing to decreasing, or from decreasing to increasing. If there's no change of increasing, decreasing behavior, then there's no maximum, minimum. For example, if you have a graph that's increasing and keeps increasing, you can see this location is neither a maximum nor a minimum. All right, so we cannot tell. So nothing. So next, around 1. Let's follow the arrows. Left graph increases, right, the graph decreases. So going over location 1, graph goes up and down. So we expect a maximum here. Maximum value. So 2 is the maximum value. Critical point value is the location. Okay, when they say find the maximum value, minimum value, you're going to say 2 or -2, not the critical values, 1 or -1. Okay, 1 or -1 are just location is on x-axis. This is x-axis. All right. So this is how we apply the first derivative test to detect any local maximum or local minimum at each critical point. All right, there's more. Okay, so let's talk about the second derivative test. Second derivative test is another way that we try to determine local maximum, local minimum, right? It involves what's called a second derivative. Well, what's the second derivative? Second derivative is simple. It's just differentiation twice. So given a function, you can differentiate once. That's the first derivative. You can differentiate this guy again. You get the second derivative. If you like, you can do the third derivative. Just keep differentiating. That's all. There's not much to it. And we're going to see in the example how we get the second derivative. Pretty simple. All right, let's get to the result. The result says you're going to find the critical point first. Okay, it's always about the critical point. So you find there's C. by solving f prime equal to 0, and then check the sign of second derivative at the c. Well, the results are the following. If second derivative is positive, fc is minimum value. Now, when we talk about maximum minimum, it's always f itself. So f is minimum. If second derivative at this critical value is negative, fc is maximum. And we see the graph too. All right. So if second derivative is positive, we expect a cup-shaped portion of the graph here, meaning we expect the minimum lowest point on the graph. And if second derivative is positive, or second derivative is negative, we expect a cap-shaped portion of the graph here, and there's a locally maximum value here. All right, so this will be a minimum, this will be the maximum. All right, so just check second derivative. That's all there is. Okay, of course you find critical point. Let's see one example. So find the maximum minimum of the same exact function, because we don't want to do the differentiation whatever from scratch for a different function. So it's the same function. Let's use this time the second derivative test. So first find all critical points. We did. So we find for this function before, right? We find the 0, find the 1, find the -1, and then test out the sign of second derivative. Okay. So here, let's see actually how we even find the second derivative. Well, we find the first derivative, right? This is function. First derivative is 3 down 15x squared, 5 down 15x to the 4, right? This is first derivative. Now, what's the second derivative? Just differentiate this guy. Differentiate one more time. So bring the 2 down, get 30. Bring the 4 down, you get 60. So second derivative of this function is 30x minus 60x to the third power. And that's all. Now, the key is to check the second derivative, which is here, at each critical value, at 0, at 1, at -1. So we would do it here. So we would plug in 0. We would plug in this critical value for x. Okay, so here plugging, the answer is 0. The answer is 0. Value is 0. Well, if it's 0, we cannot tell. We can only tell if it's positive or negative. All right. Well, the test fails, so we don't know. Just don't know. We don't care. Cannot be tell. We would have to try something else. Let's see at 1. At 1, of course, we're going to plug in 1 here into the second derivative for x. 1 plug in, it's going to be 30 minus 60. And that's negative 30. The exact value is not important, the sign is. It's negative, right? Okay, now I don't remember what should we have. Second derivative is negative, right? Let's check the test. Second derivative is negative, the function value is the maximum. So we know this is the maximum. That's a maximum value. Okay, let's see at the third critical point, -1. -1 again, plug in for x here. -1 plug in, -1 plug in. Use your calculator. You'll find the value to be positive, or more importantly, the value is positive. When the value is positive, from our test, we can tell this is going to be minimum value. Okay, we tell maximum, minimum this way, not because it's 2 more than -2, so 2 is the maximum. That's not how it works. All right, so this is another thing we can do to tell something about graph a function, particularly maximum, minimum, a different way. It's called second derivative test. So both the first derivative test, second derivative test are used to detect any maximum, minimum at critical points, critical locations. All right. So we find out at 1 there's a maximum, at the -1 there's a minimum, at 0, which is also a critical point, nothing. Okay, so next we're going to discuss concaving structure or concavities of a function. Now the result. Okay, this is based on second derivative again. When the result says basically if the second derivative is less than 0, the graph will concave down. What does it mean? It means just the graph will bend down. All right. Let me show you a graph. Suppose you have a graph like this. So over this portion, it's concaving down. Where over this portion, it's like a concaving up, bending up. That's really what it means. And it's information we use later on to try to sketch graph. And then it's information based on derivative or sign of derivative, or precisely in this case, sign of second derivative. Okay, let's back to the result again. When the second derivative is negative, the graph concaves down, the graph bends down, concaving down. When the second derivative is positive, the graph concaves up or bends up. Okay. Now, how are we going to do it? How are we going to determine where the graph will bend up, graph will bend down? Well, to do that, we can do first learn what we call possible inflection point. So we're going to set the second derivative to 0. We're going to set the second derivative to 0 and solve. And find I1, I2 as a solution, as what we call possible inflection point. Okay, so this is like a definition of a possible inflection point. Next, how do we then determine intervals where the graph concaves up and the intervals the graph concaves down? Okay, here are the steps. 1, we find all possible inflection points, like here. 2, we create a sign chart for second derivative. This time, it's a sign of a second derivative. Say we find I1, I2, I3, 3 of them. Say we create the sign chart just like how we create the sign chart for first derivative. Okay, say it's positive over here, negative here, positive here, positive here, right? This is just a hypothetical sign chart here. Okay, if that's the case, then we can tell when the second derivative is positive, the graph will concave up here, the graph will concave down here, up here, up here. Well, that's just how we determine intervals of a concaving structure. Okay, so now you can see to determine concaving structure, we rely on second derivative. To determine increasing, decreasing, we rely on first derivative. So inflection points, you can see the new thing. The inflection points are to second derivative as critical points to the first derivative. All right, and then we pretty much follow similar process, right? Solve, divide interval into divide number line into interval, test out the sign over each interval. But here for concaving structure, we test second derivative. For increasing, decreasing back, we test first derivative. All right, let's see an example. Well, we'll need, oh, okay, not example yet. This is not example, sorry. Oh, yeah, it is. I'm sorry, jeez. All right, so here, yes. I thought I didn't have the function. So find the interval where the function concaving up and the intervals the function concaves down. Then find our inflection point. Well, what I missed is here, 4 f of x equal to, that's why I got a little confused. Oh, no, this is not a function. The function was 5x to the third power minus 3x to the fifth. That was the function. Okay, so for the same exact function, so we find the same, first derivative, second derivative, and then we can use the results obtained before. Anyway, so it's the same function, find our possible inflection points. Now, to find a possible inflection point, we're going to set the second derivative to 0. So for this function, we did find the second derivative here. So it's the same function. We find the second derivative as 30x minus 60x to the third power. All right, so here. And how do we solve it? Let's see. So we never solved it before, so I'm going to do it here. Factor out the 30x, then we're left with 1 minus 2x squared. And then set each part to 0. We're going to find x equal to 0, x equal to plus and minus square root of 1/2. All right, simple algebra. Set x to 0, set this to 0. We find possible inflection point. I called I1, I2, I3, right? So now create a sign chart. Say this is negative square root of 1/2. This is 0. This is positive 1/2. Okay. Then we test out second derivative. So the sign of second derivative over each subinterval. So we have 1, 2, 3, 4 subintervals. Okay. Pick up test point. So this section, this subinterval, we can pick up, say negative 10. Negative 10 is definitely on the left side of this inflection point. Okay, so -10 somewhere here, plug in for x in f prime, which is this. So make sure you use the correct expression. Use second derivative of a function. Pick up -10. Pick up -10, plug in for x. You can see this is going to be negative here. With a positive sign, it becomes a positive. So I can tell. If you use a calculator, you can tell too. Second derivative at -10 is positive. So second derivative at -10 is positive. Okay. And then one by one, you test out other subintervals. For example, from negative square root half to 0, you can pick up whatever value in between, say negative 0.001 somewhere here, and test out. It's going to be negative. And keep doing this, you'll find out it's going to be positive here, it's going to be negative here. So this is the sign distribution of second derivative. Now, of course, with this, our goal is to determine concaving structure. So positive concaving up, negative concaving down, positive concaving up, down. All right. So this is the concaving structure. Now, with the concaving structure known, we can determine what's called inflection points. What is that? Well, inflection points are points on the graph where the concaving structure changes. So all we need to do is to check out the concaving structure demonstrated here. See whether there's any change of concaving structure. And indeed, we can see from up to down. So crossing this location, there's a change of concaving structure. Therefore, we expect an inflection point here. And similar here, crossing 0 from down to up, there's a change of concaving structure. Here, from up to down, there's a change of concaving structure. So our conclusion, we expect an inflection point there. Inflection point is not just negative square root half. It is a point on the graph with x coordinate negative square root 1/2. Of course, you can find the y coordinate by plugging this value back into the original function. The original function here to find the y coordinate of the point, because this is the point on the graph of the original function. So you're going to use the original function to find the y value, negative 1.2. Okay, we already said that we also expect critical point, inflection point at this location too. Again, that's just the x coordinate, y coordinate. You're going to plug in the 0, the x value 0 into x here in the definition or expression of f of x to find the y coordinate, which happens to be 0 too. So this just represents point on the graph, not just x value on x-axis. Okay. Finally, we expect a third inflection point at the location square root 1/2 with y coordinate by plugging this x into x here. to find out its inflection point at this location, inflection point at this location, another inflection point at this location. So 3 inflection points. All right. All right. So finally, let's see how we can try to graph a given function based on results or features we can determine from derivative of a function, first derivative, second derivative. Okay, there are in general 5 steps. 1, you're going to determine where the function increases, where the function decreases. So find the intervals where f of x increases, f of x decreases. Now, step 2. Well, once you find the sign chart increasing, decreasing, then you can actually easily determine the maximum, minimum by using the first 2 tests as we did previously. 3, determine the concaving structure. That is to find the intervals where the function concaves up and the intervals where the function concaves down. 4, find out inflection points. Inflection points are very important because it shows us the changing of the bending of the graph, as you'll see from the example. And I can quickly show you. Suppose we know there is a inflection point on this side concaves up and this side concaves down. So that can show us like detailed behavior of the graph or change of the graph. Right? We're going to see this in the example too. And finally, utilize all this information in a coordinate system to try to come up with a graph. All right, and of course, we're going to use the same function. So with the same function, we did all of this. So I'm just summarizing everything here. Find the critical points. F prime equal to 0, solve, you find the 3 critical points. Then do a sign chart, got the increasing, decreasing, distribution, okay? The sign, then decreasing, increasing, increasing, decreasing for our function. Also, we find out because of the increasing, decreasing earlier on, decreasing, increasing, we find out at this location we expect the minimum. We don't expect anything here. Well, we expect the maximum because it's up and down. We would go over top of a hill, right? So we expect the maximum, and of course we come up with the concaving structure for this function too. So what we did was to set the second derivative to 0, find the possible inflection point, mark those possible inflection points, and do a sign. Well, I do have to emphasize that here is a sign of f prime, here's sign of double prime. All right, we created a sign chart here for second derivative, and the result was that it was positive here, negative here, positive here, negative here, which means concaving up, down, down. And consequently, at this location, we expect inflection point because of change of concaving structure from up to down, and here and here. We just did that earlier. So, of course, step 5. So this is the last step. Step 5, we're going to try to graph this function based on what we obtained, right, in all different parts, different steps. So first, usually we label important locations like critical points. -1, 0, 1. Of course, we're going to make use of the result that it's decreasing over here, it's increasing between -1 and 0, it keeps increasing and so on, right? Before we get that, let's actually mark the maximum minimum first. So from this part, we find out there's a minimum at the -1. So exact location is -1, -2. So mark that. At the -1, -2, suppose this is -2. The units on y-axis and the unit on x-axis don't have to be the same, okay? So anyway, so this is, so say this is a -1, -2. There's a minimum value. This minimum value, what it means is the graph would have this kind of shape. So put a little cup here, minimum. Now we expect a maximum value at 1, 2, maximum at 1, 2. So at 1, the value is 2, and this is the maximum value. So let's again indicate it in the coordinate system. At 1, there's a value 2, which is supposed to be a maximum. Since it's supposed to be maximum, we put a little cap here. Okay, so this cap will kind of help us or guide us in trying to get accurate sketch of the graph. Okay, inflection points are important too. So you see, we first locate, mark, this label, these important points. We detected inflection points at the 3 locations: -√1/2, 0, +√1/2. Okay. So -√1/2 is not less than -1, it's more than -1. So let's just hypothetically say it's somewhere here. Say -√1/2, there is a +√1/2, and there's 0, the same location, 0 there. All right, so we expect inflection point at this 3 locations precisely -0.5 with the y coordinate -1.23. So let's kind of mark it here. So there is an inflection point here, there is an inflection point here, there is an inflection point here. When we try to graph, we're going to try to reflect the fact that those locations are inflection points. All right, so now let's check out the increasing, decreasing, concaving up, concaving down features. So let's say in general, from -infinity to -1, the graph is going to decrease. So -infinity to -1, the graph is going to decrease. We're going to kind of, let's use the red color. We're going to kind of draw a graph like this. It's decreasing. From -1 to 0, the graph will increase. Actually, the graph will increase from -1 to +1, right? But let's also take into account the fact that the graph on the left side of 0 is supposed to concave down. on the left side of a negative square root 1/2, the graph is concave up. So we expect then concaving up, graph bending up, bending up, bending down, or still increasing, see? So from -1 to 0, it's increasing, but with the concaving structure, we can fine tune our graph as up and down. Let's check again, up and down, okay? So similarly, between 0 and 1, the graph is going to increase. It's going to increase in such a way that the graph will concave up from 0 to square root 1/2, and then on the other side of a square root 1/2, the graph isn't concave down. Therefore, we're going to do concaving up, concaving down. As a matter of fact, it's concave down all the way, which also reflects the fact that the graph is decreasing from 1 to positive infinity. It's decreasing from 1 to positive infinity, right? So you can see here, you can double check everything. And this is how we come up with the graph. Minimum, maximum, decreasing, increasing, decreasing. With the concaving structure, with the inflection point, we can even detect, fine change of the graph, concaving up this section, concaving down this section, up, down. All right. So this is how we try to rely on derivative function to analyze the graph or feature of a graph of function, eventually sketch graph of function. Let's stop there.